last few modules we are talking about angular momentum, and I have introduced you with the angular momentum, orbital angular momentum, spin angular momentum, and the ladder operators, and all those concepts, commutation relationships. All these concepts we have covered. Now, if it's a one electron atom, this was the slide where I left you in the last module, that if you have a one electron and you operate with an LZ operator on a function ylm, where ylm is the spherical harmonics, then what you get, what is the eigenvalue is mlh cross. Okay, and this ml is actually magnetic quantum number. With somewhere I've written m, somewhere I'm writing ml, so don't get confused. And if you operate with L square operator, the square of the total orbital angular momentum, then the value which you get for eigenvalue is L into L plus 1 h cross. Okay, this L we also saw the value of magnetic quantum number is decided by the azimuthal quantum number. Okay, so this also we saw in the last module. And if L is equal to 0, 1, 2, 3, we write as PDF. If it is a multi-electron atom, in case of many electron case, also you get this one, but the only representation is changing. You see ml becomes ml, capital ml, okay, and this L becomes capital L. If capital L is 0, 1, 2, 3, then you have capital S, P, D and F. These are designations for the spectroscopic term symbol we will talk about later on. But even in case of one atom, you have orbital angular momentum and spin angular momentum both. I said you that spin angular momentum is a purely quantum mechanical concept. It doesn't have a counter property in classical mechanics. Okay, so we will talk about that how does these moments, orbital angular momentum and spin angular momentum, will interact with each other. So that's called LS coupling, spin orbit interaction, or Russel Saunders coupling. Okay, there are many. These are known by several names. So Russel Saunders coupling or spin orbit interaction we are going to talk about. When a spin orbit interaction will take place, there will be a potential energy which will develop, and that potential energy will change the Hamiltonian of the hydrogen atom, because till now what the Hamiltonian of the hydrogen atom which you have used is minus h cross square divided by 2m del square plus minus E square by r. E square by r is the potential energy. This potential energy is also because of the electrostatic interaction between the electron and the nucleus, and the first term is the kinetic energy. So whatever kinetic Hamiltonian we have used till now is the Hamiltonian for related to Coulombic interaction. Now we are going to see that what will happen if you place a hydrogen atom in a magnetic field. But before that, just a background information. So I am taking it from the very basic, that if you have an electrical charge and which is moving in a closed loop, then it will produce a magnetic dipole. And this magnetic dipole, again I am representing with the same sign M. So don't get confused with the symbols. Now I am using M for magnetic dipoles. So magnetic dipole M is given by I into A, where I is the current in ampere and A is the area of the loop. So this is the basic physics. Everyone knows that a moving charge particle in a circular path will produce a magnetic field, magnetic dipole. So this is a magnetic dipole. Now this circular loop, for a circular loop, this I ampere current can be given as charge into velocity divided by 2 pi r, because it's a circular path, so it's 2 pi r. Now if you use this equation, where V is the velocity, Q is charge and R is the radius, then this magnetic dipole becomes equal to QV divided by 2 pi r multiplied by A, area of the circle is pi r square. Okay, so this becomes QVR divided by 2. So this magnetic dipole is QVR by 2. Now angular momentum L is given as R into P. The basic definition, the first slide, the first thing which I talked about, and P is equal to mass into velocity. So what is velocity is what? L divided by mr. We can write. So if you introduce this term, angular momentum in the equation number 2, what do you get? Magnetic dipole becomes equal to Q divided by 2m into L. So we are again back to the orbital angular momentum L, capital L sign. Okay. So magnetic moment is controlled by angular momentum. That's the equation 3 tells you. Okay, of a circularly moving electron. Now for an electron, if I place mass of the electron as me and charge q of the electron as minus e, then what do you get? The equation is magnetic dipole m is equal to minus e 2me into L. So the equation 3 changes to this one. So if you have an electron moving in a circular path and you place it in a external magnetic field, then this magnetic dipole of the electron will interact with the external magnetic field, and this interaction will produce a potential energy, and that potential energy is given as V is equal to minus mb, where m is the magnetic dipole, magnetic moment of the dipole, and b is the external magnetic field. Okay. Now, if this where this where this magnetic field strength is defined by F is equal to V into B. V into B, where F is the force, Q is the charge moving with the velocity V, and magnetic field strength is B. Okay. The SI unit of B is Tesla, and you can find out 1 Tesla is 1 Newton per ampere meter. Okay. So assume the direction of the magnetic field strength to be Z direction, then this potential energy will be V minus mz into Bz. Okay, component of the magnetic field strength in the Z direction, component of the dipole moment, magnetic dipole in the Z direction, and the potential energy will become V is equal to minus mz Bz. If you replace this velocity with in equation number 3, then what do you get? Equation mz becomes equal to minus E. Just replace the Z, for the Z direction, equation 3 could be written as mz is equal to minus E 2me Lz. Now potential energy is V is equal to minus E divided by 2me Lz Bz. Potential energy V is equal to minus mz Bz. So potential energy becomes equal to minus E divided by 2me Lz Bz. Replacing Lz by a corresponding operator. Now till now we have a component of angular moment, a physical variable, component of orbital angular momentum in Z direction. Now from this physical variable we are going to operator. So if you represent this component Lz by an operator, then the potential energy will become minus E 2me Lz Bz. Okay. These are very basic physics. So this potential energy which arises because of the movement of the electron in a circular path will change the Hamiltonian of the hydrogen atom. And the new Hamiltonian of the hydrogen atom will be a Hamiltonian in absence of the magnetic field, and this part in the presence of the magnetic field. Okay. So H0 is the Hamiltonian in absence of the magnetic field, and H is the Hamiltonian in presence of a magnetic field. So when you place a hydrogen atom in a magnetic field, the Hamiltonian does not remain same. And this you have learned from 10+2, that whenever you take a hydrogen spectrum in electric field or magnetic field, there is a splitting of spectral lines, which is a Zeeman effect and a Stark effect. Okay. So now see the potential energy we are changing. So the energy diagram of the hydrogen atom, which we have learned from Bohr's model or from the derivations we talked about, will also change because the Hamiltonian we have changed. Okay. Now, in absence of a magnetic field, the eigenvalue equation is H0 psi is equal to E0 psi. Minus sign only tells you that the energy is negative, and you know it's if you take 1 0 0 1s orbital, then the energy comes out to be minus 13.6 electron volt. So minus sign is only telling you that the energy is negative. Okay. So in presence of magnetic field, what will happen? Your Hamiltonian will now change to H0 minus E Bz 2me Lz into psi Lm. So the eigenvalue equation, the right hand side of the eigenvalue equation will also change, and it will be minus E0 plus E Bz 2me ml h cross. Now ml h cross means you are operating with Lz on psi NLM. So you remember that if you operate with Lz on phi, what do you get? You get m h cross phi. So this m h cross we have used here, ml h cross. Okay, psi NM. That's what we, because this is equal to this one. Okay. Now if you so what is your energy value? Energy value is now E is equal to minus E0. Now I am representing E H cross divided by 2 me by a new symbol beta B. Okay, so E H cross 2 me I have written. So what it remains? ML and BZ. So ML and BZ remains. This quantity beta B is called Bohr magneton. I'm sure you have heard it earlier, but the actual quantitatively it is this value, and Bohr magneton comes out to be 9.2740 into 10 to the minus 24 joule per Tesla. Okay, so this was known to you. Simply, what we are doing, we are treating a hydrogen atom placed in a magnetic field. And I said you that because of the orbital motion, there will be a magnetic dipole, and that dipole will interact with the external dipole, and this interaction will change the potential energy, and if it will change the potential energy, it will change the Hamiltonian also. So that Hamiltonian we are talking about. Okay. Now, the equation ML, from this equation, the magnetic moment because of the orbital momentum is given by this equation number 4. So what does it mean? If you operate with L square and psi and Lm, what do you get? Again, these two operations you always remember that if you operate with this one, you get L into L plus, L into L plus 1 H cross square, okay, into phi, whatever be the wave function, this you get. Okay, so what is the L value? L value will be a square root of L into L plus 1 into H. So that the L value I put here, ML becomes equal to minus E H cross 2me L into L plus 1 raised to the power half. So H cross comes here, and this one is the eigenvalue of L square. Okay, from this equation we can write equation 5 like this one. And now if equation 5 is this one, so again Bohr magneton can replace this quantity minus E H cross, and ML will become equal to minus Bohr magneton L into L plus 1 raised to the power 1 by 2. So this is the magnetic moment because of the orbital motion. Exactly in the same fashion, since an electron has a spin motion also, so you can think of a magnetic moment because of a magnetic dipole because of the spinning motion. And this spinning motion, if you write exactly in the same way as you have seen that all the relationships of commutation and everything, we just have written in the form of a spin for the spin angular momentum also, without doing any derivations. In the case of a spin angular momentum, I just copied all the orbital angular momentum relationship to a spin angular momentum also, because it's valid for both the cases. Okay, so if you here also, if you write the magnetic dipole because of the spin, then it becomes exponential G E 2me into S. The only new quantity is G, okay, which I will tell you, and this ms will become equal to, in the same fashion, G beta B S into S plus 1 raised to the power 1 by 2. Okay, where this G is equal to 2 appeared naturally in relativistic extension of quantum mechanics by Paul Dirac. So when Paul Dirac derived this, extended the concept of quantum mechanics to the theory of relativity, he found the value of G, and this value is equal to 2. So MSZ is equal to, so this is your, actually it should have been like this one, MSZ, Z component of the spinning moment. Okay, so this will, you will replace S by SZ, nothing else. Okay, rest of the thing is same. So this becomes equal to minus GE 2me MS. Okay, so in case of LZ operated on phi gives you MH cross phi. So in case of SZ operated on phi will give you MS H cross into phi. So this relationship we have used. Okay, same thing we are extending it to the spin momentum. So it's MS H cross, and now you can write minus G beta B into MS, because this will be beta B, so minus G beta B, and this we say is unit called plus minus beta B, And what I've written is, in the Stern-Gerlach experiment, the two projections of the beam occurred at position consistent with the magnetic field. So this theory actually explains the experimental observation obtained by Stern-Gerlach experiments, and this is the origin of the spin angular momentum in quantum chemistry. I said you it is an experimental observation. Theoretically, there is no analogy by which you can explain the spin of an electron. It's purely experimental concept. Theory came later on when Paul Dirac extended the idea of this to the relativistic quantum mechanics. Okay, so this we obtain. Now, if the Hamiltonian of a hydrogen atom, which we have used till now, is what? Hamiltonian, this is your kinetic energy part, and this is your potential energy part. Okay, and this potential energy rises because of the force acting between E square by R square, 1 by 4 pi epsilon, of course. Okay, this is the charge. This force is Coulombic interaction. Okay, so this here you do not have any other potential energy or kinetic energy. The only interaction is a electrostatic interaction. So whatever the relationship which we have used for Hamiltonian is an electrostatic interaction only. But since we have seen that there could be an interaction between the orbital angular momentum and the spin angular momentum, two magnetic moments within the nucleus, within the atom, then magnetic moments of the orbital moment and magnetic moment of a spin angular momentum interact with each other because they are dipoles. So like any other two magnetic, they will also interact, and they behave as a magnetic dipoles. So this interaction also must be added into the Hamiltonian, and that part, if you add, this is called LS coupling, Russell-Saunders coupling, or interaction between the orbital and spin angular momentum. Okay, so it will be given by an additional term in the Hamiltonian. It means it will change the potential energy or the total energy of the system. Okay, and means Russell-Saunders coupling is responsible for changing the energy levels of the hydrogen atom, or for that matter any other atom. Okay, beside the shielding and all those things. But since orbital angular momentum and spin angular momentum are inherent properties, so they will change the properties of the system. Okay, here xi r is some function which I have not explained. If any one of you is interested, one can see it's given in the problem form in Macquarie's quantum chemistry. Okay, so if any one of you is interested, what is this function, then you go and see the problems in the I think I don't remember the problem number, but it is given in the Macquarie. Okay, so this is the but remember that we have added new term to the Hamiltonian of the hydrogen atom. Okay, now what we say that when these interacts, the spin angular momentum and the orbital angular momentum also add to give you a resultant angular momentum, total angular momentum, that is denoted by a symbol J. So when a spin orbit interaction is taken into account, L square and S square no longer commute with H, and so L and S are no longer conserved. Only the total angular momentum J is equal to L plus S is conserved. Okay, so total angular momentum concept we will talk about. It means whenever you have two sources of angular momentum, whether a spin or orbit, or two orbital momentum, or two spin angular momentum, that I am not talking. I am just talking about that you have two sources of angular momentum, and then they could be added to give you the resultant orbital angular momentum. So addition of angular momentum tells you that if you have two different sources of angular momentum, one could be a spin, another could be orbital, or both could be orbital, or both could be a spin, then they could be added to give you a resultant angular momentum. So the resultant angular momentum, if you have two electrons, that gives you a J1 and J2, then the resultant angular momentum is written as J and J1 plus J2, capital J. Normally it's shown as a capital J. Now what will happen with this capital J resultant angular momentum, will this property, the property of this resultant angular momentum will be different from the orbital angular momentum or spin angular momentum? Will it follow all the relationships which we have done earlier for the orbital angular momentum or not? Then let me tell you, it will follow every relationship. In case of orbital angular momentum, what I have written, L square is equal to Lx square plus Ly square plus Lz square. This was L square. So J square will be Jx square, Jy square and Jz square. Okay, same relationship. The only symbol is changing, and now we have resultant angular momentum instead of orbital angular momentum. Now this Jx again is what? Here it has two sources, from one source, from another source. So it will be Jk will be J1k plus J2k, or if you don't write J, then J is equal to J1 plus J2. Okay, K is for the x, y, z. So Jx will be J1x plus J2x. X component of the first orbital angular momentum and x component of the second orbital angular momentum. You sum it up, you will get Jx. Okay, so that is how it is following the relationship for the same relationship which we use in the angular momentum. What about the commutation relationship? We have seen that commutation relationships are very important, and the two commutator relationship which is important, I said you, is L square Lz is equal to 0 and Lx Ly is equal to I h cross Lz. Okay, and same way Ly Lz and Lz Lx all I have written. Okay, so if you look at this equation which we did earlier for the orbital angular momentum, it is same for the resultant angular momentum also. There is a resultant angular momentum in x direction, resultant angular momentum in y direction, and this gives you this. They are not commuting, commutator for the resultant angular momentum. So they are not commuting. It is giving I h cross Lz. It means it will follow the first commutator relationship also. Okay, and it will follow. It does follow the first commutator, J square Jz is equal to 0. Okay, so all the relationships in the orbital angular momentum which we have gone through is equally valid for resultant angular momentum also. And resultant angular momentum is sum of the individual angular momentum, J1 plus J2, or if you have J3 also, then J1, J2, J3. We are talking about 2 only. So if it is so, then the eigenvalue equation which we have used in case of orbital angular momentum, that should be valid here also, and it is valid. Okay, and then J square and Jz will have a common set of eigenfunctions. That you know, if two or operators commute with each other, then they have common sets of eigenfunctions, and the eigenvalue equation will also be similar to the angular momentum of one electron. So the eigenvalue equation I have written on the previous slide also was this one. Just for the simplification, I am writing phi. This will be equal to mh cross phi. Okay, and Lz L square. L square, when operator on phi, it will give you L into L plus 1 h cross and phi. Okay, so these relationships, eigenvalue equation, will be followed for J also. For Jz into phi will be mj h cross phi, and then J square into phi will be Lj into Lj plus 1 h cross. So same relationship. J is the quantum number for resultant angular momentum, and mj is the quantum number for its z component. Okay, so same way you can write, and as earlier, J can take integral and half integral value. So L can take integral and half integral value, so J also can take these values. Okay, since J square and Ji commute, so J1 and J2 can also be specified along with J. Okay, now this is the relationship which is different, that we say J square and J I, means first and second, it could be this, they commute, this is equal to 0. So what does it mean? It means J1 or J2 can also be specified with the resultant angular momentum. So this is different because this we never came across, the first component and second component earlier. Now, since now we are doing addition of angular momentum, so now we can say that the two angular momentums which we are using can be combined together. Okay. So this addition of angular momentum is these two slides are just the concepts that how do we add angular momentum to get the resultant angular momentum, and it means this addition is allowed, and this addition follows all the rules of the angular momentum algebra. Okay, that commutation relationships and everything which we did will be followed. Now these two, J1 and J2, I said you are coming from two electrons, but not necessarily two electrons. It could come from one electron. One J1 could be angular momentum of the orbital angular momentum, and another J2 could be the spin angular momentum. So they two can be combined, and that's what is called LS coupling. Okay. So addition of LS coupling is basically the concept of addition of angular momentum. Okay. And I said you that this angular momentum, since there are two angular momentums, so in a magnetic field, this angular momentum will influence the energy diagram of the hydrogen atom, or for that matter for any atom. Okay. Now, how do we represent this angular momentum? In case of a multi-electron atom, we assign a spectroscopic term to a specific configurations. Okay, we assign a spectroscopic terms to a specific configurations, and these spectroscopic terms can be arranged in order of increasing or decreasing energy levels. Okay, these are the concepts which arises from the quantum chemistry, but very widely used in case of coordination chemistry. If you look at the coordination chemistry, then these spectroscopic term symbol are very widely used because they gives you the spectral properties of coordination compound. Okay, but let me start this spectroscopic terms in the next module, because this module will be a little longer if I continue it here. Okay, thank you.